are Team Dronedash, a computer engineering senior project design team of California State University, Long Beach, and we are here to showcase our autonomous delivery rover.
For our payload subsystem, we decided to go with a electro-permanent magnet servo called the Flux Grip. Issuing a command through PWM, we are able to send a signal to attach and detach the payload from our vehicle. Now we'll be showcasing the attach and detach. So now it is attached, and I will be issuing the detach command.
Now that we have achieved our manual control system, we are now ready to integrate our autopilot and navigation. For our autopilot navigation system, we have three essential components. We have our P-Hawk 6X flight controller. What this does is it calculates throttle and steering movement to navigate the rover to the location it needs to go to. Attached to it is a GPS module. It reads GPS coordinate data of the rover and sends those data to the flight controller for the flight controller to make the necessary movements to go to the desired location. These two can be controlled in a GUI software called Mission Planner, and we can plan missions there to control autopilot of the rover. Now, one more essential component to the rover is its companion computer. We are using an NVIDIA Jetson Nano board. What this does is it can eliminate the need for a GUI software. All that we need to do is just build a script to make the whole functionality of the rover. It also enables networking, and it communicates to the flight controller via Mavlink.
For the computer vision subsystem, we're using the Intel D435i camera for visual and 3D visual depth for mapping environment and proximity data.
Now I'll showcase our camera subsystem for a ground vehicle. Right now we are hooked up on the camera to the companion computer, and I started an RTX server, and now we will conduct a camera test. So as you can see, Mark is standing in front of the camera subsystem, and you can see the proximity data here. Mark, can you take a step back? As you can see, Mark is moving back, and the proximity data reflects that movement. And as he moves forward, you see the proximity data get updated. That concludes our camera subsystem test. Thank you.
We are using a Mission Planner software, and to show the autopilot navigation system of the rover, this is how we test it. This is the rover on map, and the compass heading shows the rover is facing this way. Now, we already set waypoints of the map 1, 2, 3, and we expect the rover to move on those directions and go back to the home location. Now, once we're done, we just write the data, and we set the mode to guided, and we can start our mission. We can also monitor the rover as it moves. And we set the mode to guided, and we can start our mission. We can also monitor the rover as it moves.
In our movement subsystem, we used two different kinds of motors. We had the brushless motor and a brushed motor. We actually started with this car in our testing. Now, as you can see, if I apply a small throttle to it, it goes really fast, not stable, which is not what we need for the purpose of our delivery rover. Now we switch to a brushed motor setup, and once I apply a small throttle to it, it's slow, stable, controlled movement, which is essential for what we need for our delivery rover. Now, to put the motors to the test, we'll show a drive test by having the two cars in a race. 3, 2, 1, go. As you can see, the brushless car is really fast, while the brush motor is barely slow, which is what we need for our project. We don't need to be fast, we need to be in a controlled, stable movement.